Okay, today we're going to do our next lesson on transformation. So the first one was on horizontal and vertical translations. So that moved things left, right, and up, down. Today we're going to look at horizontal and vertical stretches. So that means we're going to take the graph and make it taller or shorter or wider or narrower. Okay, so again, let's start with a quadratic look again. So you can see this original red graph is x squared minus 2, so just a regular quadratic that's been shifted down 2, and we can kind of review that from yesterday, right? Y equals x squared would just be a regular quadratic, something like that. So the minus 2 part is going to move that down 2. So we've already actually done a vertical translation, but now we're going to take that red graph and do a vertical stretch on it. So you can see the half in front is going to make the blue graph half as tall. But more importantly, it's not just the graph itself, you've got to look at the coordinates again. So this coordinate, this vertex that's at -2, if we cut it in half, it's going to go to -1. And you can see this coordinate that was at 0, an x coordinate of 0, y coordinate of 0, x of about -1.5 or so. If we cut that in half, it stays the same, because half of 0 is still 0, and the same thing on the other side. And if we pick some other coordinate, let's suppose we had something like -3, 6. If we cut that in half, it moved down to about -3, 3. So all of the coordinates are now half as much. So you can see the vertical distance is now cut in half. So we would call that a 1/2 vertical stretch. So we'll start from the beginning, and we'll get back to that in a second. So remember, with translations, we said the graph stayed exactly the same. So if I started with a quadratic and we moved it left, right, and up, down, the graph itself stayed exactly the same shape and orientation. It just went over a certain distance and up or down a certain distance. Now with a stretch, the graph is going to look distorted. It's going to look taller and skinnier. It's going to look shorter and wider, and so on. So a vertical stretch will take that graph and make it shorter or taller. A horizontal stretch will make it look narrower or wider. And in some cases, when you look at a picture, you might not know which it is. They might look very similar, right? If I took a graph and made it look taller, it would look something like that, right? If the original was, say, a little bit wider like that. So is that graph taller or is it narrower? Well, it's both. So is it a vertical stretch or is it a horizontal stretch? It could be both. And that's where you got to be a little bit careful with stretches. Sometimes you can kind of get two different things describing the same situation. So we'll start with vertical stretches because, again, they tend to be a little bit easier. So when we're looking at our equation, the vertical stretch is the number out front. So again, let's kind of go back to quadratics. So last year you would have looked at something like 2 times x plus 3 squared minus 4. So we already dealt with the 3 and the 4. That was, in this case, would be left 3 and down 4. So today what we're going to figure out is what's the 2 value doing. So that 2, we'd call it the a value in terms of our formula. So it's a number out front of the equation. Or, again, we could flip it to the other side. So if I wanted to, I could move this 2 over, and we would divide by 2 on both sides. So we could write this as a half y instead. So it doesn't matter which way it's written, you just got to, again, be comfortable moving those numbers back and forth. So yesterday we were moving the number to the other side, like the 4, we can make that, move it over, and that'd be plus 4. But today we're going to be getting rid of the multiplying by 2, so we'd have to divide by 2. So watch for where that value is, but again, it's still timesing the entire equation by a certain value. So we'd say that's our stretch value of a, whatever the number is, in this case 2. And, oops, I messed up, our coordinate, if we're going to times our coordinate by a, or 2 in this case, that means our y coordinate gets multiplied by 2. Let me just put that in here as red. So I missed that when I typed it. Okay, so our a value would just multiply that y coordinate, whatever it is. Okay, so for example, let's just say our starting coordinate was 3, 4. And we're going to do a vertical stretch of 2. Our new coordinate then would be 3, 8. Okay, if we did let's start with the same coordinate again, 3, 4, but now we're going to do a vertical stretch of a half instead, then that would change to 3, 2. So you can see when you have an a value larger than 1, that's going to make the graph taller, and that's when we went from 4 to 8, made that point move upwards. If we have an a value less than 1, but it's got to be greater than 0, otherwise we get into negatives, and we'll deal with that later when we get to reflections. But if our a value is less than 1, so a fraction like a half, a third, a quarter, something like that, that's when we're going to get a shorter graph. So you can see here our coordinate went from 4 down to 2. Okay, so that's what this little picture is showing you. Any kind of a value, like a half or anywhere between 0 and 1, that original a gets pushed down shorter. Any number bigger than 1, like a 2, the a value gets twice as tall. Okay. One other point in here, it says it has to be greater than or less than 1. It can't be equal to, because if it was equal to 1, like if I made a 1 in this equation, well, the 1 doesn't do anything. It's unchanged. So in order to make a stretch, it's got to be bigger than 1 or less than 1. We can't stay at 1. Okay, horizontal, again, works very similar, except it's now inside the brackets. So this is a type of equation that we didn't do last year. So if I gave you something like f of 3x, right, we just said a vertical stretch is when the 3 is out front. So this one would be 3 times vertical stretch, because the 3 is out front. Now we're going to move that 3 on the inside with the x. That's where we deal with a horizontal stretch. So we use b for the indicator number for the horizontal stretch in our formula, and that b value is going to make it wider or narrower, and it's going to only affect our x coordinates. But remember, just like when we did left and right, the sign was sort of opposite. If we had a +2, we actually went to the left. It works kind of similar with stretches. If we actually put a 3 inside the brackets like I have, that ends up actually being a 1/3 horizontal stretch. So instead of doing the opposite sign, we do like the opposite refraction. We do a reciprocal of that number. So if the b is 3, we do a 1/3 stretch. If the original was something like a quarter, when we flip it, it would turn into a 4. So just like we did with the last one, our x coordinate will be affected by whatever that b number is, but we have to do the flip of that number. Okay, so if b is 3, we're doing a 1/3 stretch. And again, if you look at it here, if b is less than 1, you can see the 1/3 stretch will actually make that thing wider. Sorry, let me kind of backtrack here a little bit. If our b value, so b of 3, right, if our b is 3, that's something like over here, that's a 1/3 stretch. You can see the width of that b went skinnier because we had to do that flip. If the b value was something like a half, then when we flip it, that would give us a stretch of 2. So you can see that's what made this b value twice as wide as the original. Okay, so it works the same as vertical stretch. You just got to watch for that the reciprocal of that number. Okay, so let's kind of go back to this original graph again. So we already decided that it was a vertical stretch of a half. So that means every y coordinate got cut down in half, and we already looked at that, which made sense, right? The -2 went to -1. The 0 stayed the same. The other coordinates, this one was at -6, went down to -3, and so on. Okay, so we actually did our vertical stretch. So our xy coordinates changed to x and 1/2 of whatever the y value was. And you can see that every coordinate moved except for these two right here. And those two, we use the term invariant points. So anytime we're doing vertical stretches, the invariant points will typically be the x-intercepts, because there are 0, half of 0, or 3 times 0, whatever that a number happens to be, will still be 0. So you can see our domain and range kind of work the same. So our original graph had a domain and range. The domain was any real number. I'll do it the old way. And our range was greater than -1, greater than or equal to. So now you can see in our stretched graph, it got squashed up and down, but our domain didn't change. It's still the same, and our vertex now is at -1. Oh, I did that backwards. The blue one was the original graph. It's at -1. Or sorry, the red one was the original graph. Its range was at -2. And then we cut it to a -1. But you can see that from the red to the blue, it is exactly half as much in terms of our domain and range as well. Okay, so when we do horizontal stretches, here's another graph. You can see, let me kind of sketch. It's hard to sort of see these ones. So here's this red one that I'm drawing now is our original graph. Okay, so you can see this first one, I'll recolor it here. So this first one that I'll draw in green is f of 2x. You can see the 2 is inside the brackets. So f of 2x would mean horizontal stretch of a half. Remember to flip that number. And you can see I've got a coordinate here. This coordinate that was at -2, it moves over half as much. It moves over to -1. Okay. This one over here that's at 4, it moved over to 2. So you can see all of the coordinates have actually changed to half as much. The one coordinate that didn't change is the one that's right on the y-axis because it's at 0. The x-coordinate is 0. Half of 0 is still 0. So all of our x and y coordinates, the x-coordinates moved half as much. By having that 2 in the equation, it cut the x-coordinates in half. Okay, and let's do the last one that's shown here. You can see it's hard to see the decimal, but the equation is 0.5x. So f of 0.5x, and you can see, so if that's 0.5 or a half to start with, that'll make a horizontal stretch of 2 then. It's going to be twice as big if we do the reciprocal of a half. So all of our x and y coordinates should be twice as wide. So again, if we go from the first one, the original red one here is at -2, it's now moved to -4. The one over here, let's go down to this bottom one. The original one was at -1, or +1, it's now at +2. So again, you can't really see this one, but if we extended the graph, this one would now be over twice as much, over to 8 as well. So it works the same way, just got to be careful of that fraction thing. So again, our domain and range, the original graph looks like it went from -1 to infinity. And our range was, oops, sorry, that was the range. The domain is any real number. We'll assume those graphs go on and on forever. So we'd say from -infinity to infinity. So now when we do these stretches, the range will be the value that's affected. The domain still would be any real number for both. It doesn't really matter. And our range would be whatever our stretch is. If we cut that one in half, or sorry, I'm saying that wrong again. Because we're doing horizontal stretch, our domain will be wider or narrower, but because it goes to infinity, it stays the same. You can see all of our ranges are still down at -1 because that's vertical, so the range stays the exact same in both cases. So in terms of our domain and range, nothing changed. They're the exact same in all three of these graphs. So in terms of a change in domain and range, it would be the domain that would change, but that would only happen if the graphs ended. So if all of these graphs stopped at the top, then they would be a different domain. Okay, so let's do one more example. So this one here, we've got just a generic function. So you can see on the graph we have this sort of triangular shaped function, and it's asking us to do a transformation of 5f(3) of x. So you can see in words below I've got written, we have a vertical stretch of 5, and then we have a horizontal stretch of 1/3. And when you're trying to figure these out, you can do them in steps. So we could do the 5 vertically first. That means our x would be 5, our x would stay the same, and our y would be 5 times bigger. And our horizontal then would then be 1/3 as much. So you can do it in steps. You could even do it in the other order. We could do the x of 1/3 first, and then the 5 on the y second. It really makes no difference. What a lot of people do is just jump right to the combination. So we would even avoid this step. So we're just going to take 0, 0, times them by 1/3 and 5, they would stay at 0, 0. So if we put that on our graph, that coordinate would remain invariant. It doesn't change. 3, 1, once we times it by 1/3, it would be 1. The 1 times 5 would be 5. So now this coordinate would be 1 over and 5 up. So somewhere about there. Let's keep going. The next coordinate on here is 6, 0. Times it by 1/3 would be 2. Times it by 5 would still be 0. So that's about there. So you can kind of see, I'll draw this triangle in. That's the whole first half of the graph. So let's just do the last two. It would be 9, -1. So 1/3 of that would be 3. Times 5 would be -5. So that's down about there. And the last one is at 12, 0. So 1/3 of that would be 4, and 0 stays the same. So if I connect the dots, there's our new graph. So again, if we kind of compare each part of it, does it look like it's a vertical stretch of 5? Yeah, our original domain and range went from -1 to 1. So I'll do that first. The range went from -1 to 1. It's now changed from -5 to 5. We did a 5 times vertical stretch. The domain, the original domain was 0 to 12. We did a 3 in the equation, which was a third, so that means we times those numbers by a third, so we went from 0 to 4. And you can see, that should be square brackets, so you can see on that graph I drew, it did go from 0 to 4. So that's pretty simple. Once you kind of get the idea of what you're doing in terms of the fractions and multiplying, it's just simply do that multiplying or dividing of the numbers. And the last point I have on here is what's the invariant point. You can see the only point that didn't change in the graph is the origin, 0, 0. Every other coordinate is either moved left by cutting it in a third, or they went up and down by stretching it. Even though these two are still on the x-axis, the 2 and the 4, they had moved from their original location, so they are no longer invariant. Okay. One last thing I want to show you. I just want to see if I can add a page here quick. Yeah, there we go. Sometimes you'll get an equation, so let's just do a couple quick examples of horizontal and vertical stretches when you have an equation. So when you have the numbers like we had, it works pretty good with coordinates, but some people struggle with an equation. So let's just start with an actual function of, here I'll write it as f of x. So let's suppose we have just a linear, let's start with a linear function. So if I have f of x equals 2x minus 3. Okay, I'll kind of sketch that out. So that one would be, if we plug in some coordinates, plug in a 0, we'd be at negative 3. Plug in a 1, we would be at negative 1. Plug in a 2, we're going to be at positive 1. So we'd have a straight line, something like that. Okay, so that's a pretty easy function. But now let's call it g of x. Let's say our new equation is going to be a vertical stretch of, we'll just use 2. So let's say we have a vertical stretch of 2 times the function f of x. Right, so again, we could do it like we just did. We could take each coordinate and times them twice as much vertically. So the one here that's at 3, negative 3, times 2 should go down to negative 6. This one that's at negative 1 should go down to negative 2. The one that's at positive 1 should go up to positive 2, and we could resketch that graph. But we can actually work with the equation, and that's what I wanted to show you quickly. So if we have a 2 times vertical stretch, you can see in our notation here the 2 is out front. So what we can actually do is just sort of substitute our function in and just work with the equation. So the 2 out front would stay the same. We want to times that by the entire f of x equation. So we could just have 2 times 2x minus 3, or we could even FOIL that out and get 4x minus 6. So that's what that actual new equation would be. So I'll just redraw it here in a different color. So if our vertical stretch of 2 turns into 4x minus 6, and we were to graph that equation, it would go exactly through those 3 points that I just sketched out. So it would be a vertical stretch of 2, and it would just look kind of more stretched out like that. Our invariant points in this case would be at, you can see, the only one that doesn't change is that x-intercept. And it looks like it's at 1.5. So we'd have 1.5 and 0 for an invariant point. Okay, let's just do one more quick one while we're on this topic. So again, I'll start with let's just use the similar kind of equation. So if I started with 2x minus 3 again, we already had our graph. It looked something like that. This was at minus 3. That intersection was at about 1.5, somewhere in there. So that's our original graph. This time, let's do a horizontal stretch. So let's say g of x is going to be f of, let's do half this time. Let's say it's going to be half x. Okay, so the last one, let me go back to that last page. So our 2 was out front, so we said it was a 2 times vertical stretch. So we just times the entire equation by 2. In this case, because the half is on the inside, it's a horizontal stretch. And we got to do the flip, so it's going to be a 2 times horizontal stretch. So in terms of the equation, or let's do it without the equation. So horizontally, this one should stay the same because it's 0. All of the other coordinates should be twice as big. So this one that's at 1.5 should move over to 3. One that's way up here should be twice as big, and the same thing in the negative direction. So we should get a graph that kind of goes something like that. Okay, so let's work on the math on this one. So for g of x, So if we have a half in the equation, all we want to do is we want to substitute this whole thing in, this half x, put that in for the original x. So if it's a vertical stretch, we just put it out front of the equation. If it's a horizontal, we substitute it into the equation of where it is. So that half x, when we plug it in, would turn into 2 times a half x minus 3. Okay? And multiply that out. If we want to simplify it, that would just be 1x minus 3. So again, if we were to sketch this out, it would go through negative 3, it would cross at positive 3, and my x's are off a little bit, but you can see it would just be a diagonal line, something like that. And that is the correct graph of that stretch. So all of these are twice as big. This one's our invariant point in this case. Our invariant is at 0, negative 3. Okay, so when you're working with equations, vertical stretch, just times the entire equation by that number. Horizontal stretch, we times the whole x value by whatever that factor is in the equation. We don't deal with the 2, right? That's telling us what's happening with the graph. We actually got to put the whole half x in for x. We'll be doing more of this in the next couple days when we deal with reflections, but this is a pretty good first step. Okay, that's it for today, and we'll continue on the next lesson.